Let's find the finals. The final schedule. Okay, so we are Monday, Wednesday, Friday. Monday, Wednesday, Friday. Statics is at 9. So our final is the 20th.
Oh,
And yeah,
at 8 o'clock.
That's a shame. But it's a 2-hour test, so it's 8 to 10.
Can you make it a 1-hour test?
Well,
Just show.
Well, it's really up to you, I guess. You can make it a 1-hour test, but and then for the people in thermo, that's the next time slot. So that would be like 11 to 1. I already mentioned I'd be happy to let people, move to a different time. Yeah, and even if you don't take thermo, I mean, we can.
A couple thermo tests
I-
to that. We'll just jump to that when we're done.
So yeah, you could take it with the thermo people. I mean, it would be helpful to me if you're not going to take it with your scheduled one, if you take it at a different one of the, I have 3 other scheduled finals. So let's see, Monday, Wednesday so I have one Wednesday at 11, and I have one Thursday at 2, and then Friday at 8 and 11. We don't have to fit it into those, but it would make my life easier. Okay. And the next thing that I wanted to say is I believe I have now all the late work that people have emailed me. I'm still you've still turned in one weekly assignment I haven't graded yet, but things are pretty caught up, So look at your grade. Make sure everything looks the way it should. You should be able to see an overall percentage. And so you can tell unless you happen to be right near a border, you can see what your grade is. This Wednesday is the withdraw deadline. So definitely be aware of that if you think that might, concern you. And remember that financial aid can be affected by whether you withdraw. So before you just do that in this or any class, you really should make an appointment to talk to an advisor, unless you happen to know how your financial aid works with that. So, okay, I'm not trying to scare anyone or whatever, but if you're thinking about that, that's a deadline and there's nothing we can do after that. So, anybody right now have any questions about the grades or the withdraw deadline or anything like that? There are things that you can apply for, hardship exceptions for anybody who's just had, things keep coming up this semester and whatever. You can do late drops sometimes, you can have courses nullified or whatever. So all that stuff an advisor can help you with if you're curious about it. All right. So we're going back to the example we were working on Friday. Oh, before we do that, there's no school at all Thursday or Friday. And I'm canceling my classes for Wednesday. So there's also no classes of mine on Wednesday. So this is the only class this week. Okay, for me. All right. No, what did that do? Jesus. See, that's what happens when you try to be clever.
I know.
Getting a little bit of a shining vibe there. No work, no play.
Yeah. Yeah. Okay, so back to the example from Friday. And it looked like this. We had a vertical member. And a horizontal member. And a diagonal one connecting these two. And there was a frictionless contact here that made an angle of 20 degrees with the horizontal. And then we had a triangular distributed load there. I called this member 1, 2, and 3. And this was 600 newtons per meter at the highest. And this was 1 meter. This was 1 meter. And this was 1 meter. And what we calculated was F12 is equal to 0, negative 315.714. F13 is 200.398, negative 165.718. F23 is 0, negative 266.664. RD, and I better label these. So I called them A here, B, C, D. So our D was 200.398, negative 165.718, and then the scalar RB is 585.959 newtons. Okay, so one by one now we're gonna calculate the internal loads on these bodies. So we're gonna start out with member 1. And so the first step is in the coordinate system that we used for the external loads with the x-axis pointing to the right and the y-axis up, draw a free body diagram of this with the external loads on it. Okay, so use those values first. This, shouldn't take too many minutes, and just write out all your external loads on that. That's always the starting point for going to the internal loads. Okay, so here's what I got. Anybody get anything different? Same? I guess I'm mostly curious if anybody got the same thing, then I feel pretty good about it.
You got my angle wrong.
Oh, okay. So the angle is, so we're going from this to this. And so theta is negative 45 degrees. And so here's what I got after putting everything into multiplying everything by the rotation matrix. Anyone get that part? Okay, that's a good sign. And then our one cut, each one of these components of the distributed load is multiplied by x, and you can treat it like it's happening right at the midpoint. And then when you go to do your moment, the only one that produces a moment is the vertical component, and it has a moment arm of x over 2. Anybody have any questions about that? Okay. So now we're going to the second member. So take a minute and draw the external loads on member 2 before we go into the internal loads. So this is the vertical member. We have F23 up at the top. So that is 0, negative 266.664. At the bottom, we have negative F12. So that's 0, positive 315.714. And then the weight is the total weight of the member, which is 49.05 newtons, divided by the length, which is 1 meter. So we have a distributed load of 49.05 newtons per meter. Okay. For this one, let's use a coordinate system like this. It's hard to draw sideways. Okay. So now go from this and calculate the internal loads on this member. Okay. So we're going from this coordinate system here to this one. That's a counterclockwise rotation of 90 degrees, so positive 90. This is any 90-degree rotations, you could just think through this component turns into what component in the other coordinate system. It also gives you a way to sort of sanity check your answers. But I got this for my final external loads. Anybody have any questions about that? Okay, and then again, there's only one cut on this one. So our cut is valid for all x's from 0 to 1. And we have, I mean, I could write this again as a vector, just draw it out like this. But that's what that force at the left end is doing. And then at the midpoint, we don't have any vertical component, only a horizontal component of that distributed load. And when we make that a point force, it's 49.05 times x. And then the internal loads, T, V, and M. Anybody have any questions about that free body diagram? So then Newton's second law says 315.7, I'm going to round now, 71 plus negative 49.05 x 0 plus t negative v is equal to zeros. So t is equal to 49.05x minus 315.71. And v is equal to 0. This thing is just in pure tension compression, and the tension and compression just vary as you move along the length. And so when we go to the moment equation, all we have is m minus vx is equal to 0, so the bending moment is equal to 0 the whole way. Any questions about that? Okay, and then the last one, well, we don't have to use, yes?
Why is it
Mhm.
the 2-on-1, the 1-on-2 force is the one on the left and not the 2-on-3 force?
So this is member 2, and so you could do this either way. So if I look at the just whole thing to keep our bearings, so I chose for my x equals 0 to be down here.
Yeah.
And my and this to be my other end of, and so my coordinate system is like this. And so down here at x equals 0, it's the force on 2 by 1.
Okay. Yeah. Okay. Yeah. Thanks.
You could, I mean, we could have just as easily done it with the other x equals 0 at the other side, and then that would have been F23. And we would have gotten functions that look different, but any location that you plugged into the function would give the same values. Yep.
Is it only for like distributed loads that you maintain like the vector? So this case for like the distributed load really point down, and when we rotate it 90 degrees,
Mhm.
and maintain that left direction to make it positive 49, or it's still positive 49.05, right?
Well, it's going in the. It was going in our negative y before. Now it's going in our negative x.
Okay.
Um,
I was wondering, like, I was thinking about like rotating it also and having it point down.
yeah. Don't think about rotating the vector.
Okay.
Think about rotating the coordinate system around the vector. Okay. So don't think about rotating the body. Think about the coordinate system. So in this case, so the vector is going this way, which in our original coordinate system before we do this is our negative y direction.
Yep.
Then we want to rotate it into this coordinate system, right? So that same downward vector in the new coordinate system is now in the negative x.
Okay.
Yes?
If we're doing a path where there isn't any external forces except for on the about point, we can always just do the integral of v and assume the constant of integration is 0 for m, right?
That's true. Yep. That's a good point. Then you don't have your way to check it with the derivatives, but it on ugly functions that can save you time. Yeah. Okay, so now we're on the last one, and we don't have to use a rotation matrix for this one, but the calculations are messier. So this is member 3 now.
Would it maybe be a good idea to consider doing like a 180?
For sure. Yeah. It absolutely is the way to go on this. So let's just take a minute, calculate the external loads on this, draw out the free body diagram, and then I'll talk about that, okay?
Instead of rotating, why not?
I know I'm sort of cutting you short here, but let me just finish doing this, do the setup, and then I'm just going to assign this internal load problem as like the one thing for you to do for a week from now. Okay, so for member 3, over here we have negative F13, so that's negative 200.398, positive 165.718. And then at the middle, we have negative F23, so that's 0, positive 266.664. And then we have something over here that isn't going to come into the internal loads. And then we have the distributed load. The triangular one goes like this and goes up to a maximum value of 600. And then we have the uniform distributed load representing the weight. That's a total weight of 98.1 divided by 2. So we get 49.05 newtons per meter. Okay, so now we have to calculate the internal loads for this. But think about what would happen when we have that. So this is going to take 2 cuts because we have some stuff happening at the middle that we have to switch over to another function. But think about the first cut. So this is going to have this point load like this. It's going to have a distributed load like this. It's going to have the internal loads. But then the thing that makes this a mess is if you cut somewhere in that left half of this beam, your triangular distributed load isn't a triangle anymore. It's a trapezoid. Okay? And you can you can do that by breaking it up into a triangular one on top of a rectangular one, and you have to do some geometry and whatever. It's not like horrible, but it's a lot worse than dealing with it as a triangle. So we want to avoid this. So instead, just imagine going to the other side of this. And so we'll end up with, then I have to do this too. I do have to do this one at D. So our D is going, so this is 200.398 negative 34.282. Okay, so what would you see if you went around to the other side? Up is still up, down is still down. But what you used to see as left is now right, you know, and vice versa. And so now we have this force over here where the y values stay the same, but the x values are all negative. Are you with me on that? And at the midpoint, we have 266.664. And then now this is oriented in a way where if we make a cut inside of this triangle somewhere, that distributed load is still a triangle. And then don't forget about the uniform distributed load for the weight. Okay. So for the next week, like do a week from today, calculate the internal loads for this. Okay? That's all.